Okay, so today we're starting permutations and combinations. So here's our outline. So you guys have 4 lessons, a work block, review, quiz, logic puzzles, then Thanksgiving long weekend, then review, and then the test is on Wednesday, October 14th. Okay, so that'll be on the calendar, as will the quiz to help you remember. So the first lesson we're doing is the fundamental counting principle. So we're going to start with a scenario of a television game show asks participant to choose a door and then a curtain behind the door. There are 5 doors, and behind each door lies 3 curtains. How many choices are possible? Okay, so we're going to start with a tree diagram. So if we have door 1, door 2, door 3, door 4, and door 5 as our potential options for our first choice, then from each of those we have curtain 1, curtain 2, curtain 3, curtain 1, curtain 2, curtain 3, C1, C2, C3, C1, C2, C3, C1, C2, C3. So that would mean that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 different ways. Okay, tree diagrams can take a lot of time and a lot of space though, so they're not always the most efficient way to do things. So we're going to use the fundamental counting principle. So we often call that the FCP. It states that if a task is made up of several stages in which there are M ways to do stage 1, N ways to do stage 2, and P ways to do stage 3, and so on, the total number of ways to do the entire task can be represented by M times N times P times however many other options there are. So in this one, we have 5 ways to pick the door, and then 3 ways to pick the curtain, so we get those same 15 ways as we did with our tree diagram. Okay, for example, if a lock has a 3-digit code and each digit can be a number from 0 to 9, so 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, how many different codes are possible? So the way that I like to set up fundamental counting principle is say, okay, I've got 3 kind of options. I've got 3 different things that I need to choose a number for. So I set up kind of like placeholders to do my M times N times P, okay? So if I have those 3 different digit spots, there's 10 digits that can go in the first code, like spot in the code, 10 digits that can go in the second, and another 10 that can go in the third. So 10 times 10 times 10, that's going to be 1,000 codes. So to practice using the fundamental counting principle, we're going to do some exercises. So we're going to use a tree diagram or some sort of organized list or set to identify the possible arrangements for each situation. Then we're going to show the answer using the fundamental counting principle. So how many ways can an ice cream cone be constructed with 3 different scoops of ice cream flavors: strawberry, vanilla, and chocolate? Now what we're going to assume is that, and I'm an ice cream connoisseur, so I know these things, that a chocolate on the bottom and a chocolate on the top are 2 different things, right? So like a chocolate strawberry vanilla is different than a vanilla strawberry chocolate. This would be the superior scooping in my opinion, because you're eating the chocolate last. You go from like least best flavor to next best flavor to best flavor. And I live in a world where the best should be consumed last, in my personal opinion. So if you have differing ice cream flavors, you can fight me about it later. So we can do this in a tree diagram. So I'm just going to basically do the first scoop, so either chocolate, vanilla, or strawberry. And then from there, we're going to have the second scoop, chocolate, vanilla, or strawberry, chocolate, vanilla, or strawberry, chocolate, vanilla, or strawberry, because I need my first tree. And then the next one, gosh, this is going to get tight. Chocolate, vanilla, strawberry. Chocolate, vanilla, strawberry. Chocolate, vanilla, strawberry. Okay, so we can see from my first scoop being chocolate, I can either then have another chocolate and another chocolate, or another chocolate and then a vanilla or a strawberry, right? So for each of the first scoops, I'm going to have 9. So it's going to, it's tight. I should have given us more room, but hindsight's always 20/20. Okay, so there's another 9 from vanilla. Okay, so hopefully you guys would trust me that this is also going to be another 9. Okay, so we have 9 plus 9 plus 9, so we have 27 total. Another way to do this is say, okay, how many options do I have for each thing that I need to select? So first scoop, second scoop, third scoop, I have 3 options for my first scoop, 3 options for my second scoop, and 3 options for my last scoop. So 3 times 3 is 9 times another 3. So there's that same 27 different options. Okay. How many 2-letter words can be made using the words fort? Okay. So for this one, because there's only kind of 2 things going on, just like when there was only 2 things, we could do those Carol diagrams back in the first unit. For this one, since there's only 2 things, I'm going to make just a table. Okay. So I'm going to do a first letter, and that's either going to be an F, O, R, or T. And then second letter is either going to be F, O, R, or T. So second. Okay, so in this first column, my first letter is always F, and then my second letter could be F, or O, or FR, or FT. Then if my first letter is O, I could have OF, OO, OR, or OT. And I know that this words, we should put quotations around it almost, because they're not real words, but they're different combinations. So then RF, RO, RR, RT, or TF, TO, TR, or TT. Okay. So by this, we can see 1, 2, 3, 4 by 1, 2, 3, 4. So 16 different combinations. The other way that we can think about this so this was fundamental counting principle up there, just so you know. If we want to think about this one through fundamental counting principle, we want to say, okay, we're picking 2 things. For my first thing, my first letter, I have 4 different options, because remember, I'm only using those letters in fort. The second one, I have 4 different options, so 4 times 4 is 16 options again. Then how many outfits can we make if we have 3 pairs of pants, 4 shirts, and 2 belts? Okay, so same deal. Because we have more than one thing to select, we're going to use a tree diagram. So I'm going to just start with pant 1, pant 2, pant 3. And then from that, we have 4 shirts. So shirt 1, shirt 2, shirt 3, shirt 4. Shirt 1, shirt 2, shirt 3, shirt 4. Shirt 1, shirt 2, shirt 3, shirt 4. Tree diagrams are very difficult to do spacing in my world. Okay, then from each of those combos, we have belt 1, belt 2, belt 1, belt 2, belt 1, belt 2, belt 1, belt 2, belt 1, belt 2. I'm going to run out of room, but you can see kind of from each of the pant legs, get it, pant legs, there's 1, 2, 3, 4, 5, 6, 7, 8, so there's 8, another 8 here, so I trust that you trust me that there would be another 8 there, okay, but I just can't fit them. So another way to do this, so 8 plus 8 plus 8 is a total of 24. If we do this using the fundamental counting principle, we're saying we need to pick 3 things. We need to pick pants, we need to pick a shirt, and we need to pick a belt. We have 3 options for pants, 4 options for shirt, and 2 options for belt. So 3 times 4 times 2, that's 12 times 2, so 24. So same difference. This is way quicker. Okay. So if we want to use the fundamental counting principle with restrictions, things can get a little bit more complicated, but we will figure it out. So if we have 6 students in a speech class who all have to give their speech on the same day, one of the students insists on being first and another wants to be last. If the students' requests are granted, how many different ways are there to schedule the speeches? Okay, so I'm going to set up 6 kind of different slots. Okay, and all of these slots are going to be multiplied together. Okay. So somebody has to go first, somebody has to go second, third, fourth, fifth, and then last. Okay. So what this is saying is that one of the students insists on being first, right? So that means that there's only one option for that first student, right? They get that spot, because it said if their requests are granted, so they get that spot. There's only one option for that, for the number of students who can go there. It's the student who wants to go first. Then if another one wants to go last, again, there's only one option for who gets to go last. Okay. Then it's just a matter of, like, we could do random name generators. We could do whoever's birthday is closest, whatever. But there's 4 students left and there's 4 spots left. So we would say, okay, when this person's done and it comes time to pick the next person, there's 4 people, because we're not going to pick this guy. There's 4 people who haven't been picked yet. And then once someone's been picked, doesn't matter who it is, then there's only 3 left. Then there's only 2. Then there's only 1 person who has to take that 5th spot before that last person goes last. Okay. So what this means is that there's 1 times 2, or 1 times 4 times 3 times 2 times 1 times 1 ways to arrange this. So we know 1 times 4 is 4, times 3 is 12, times 2 is 24, times 1 is 24, times 1 is 24. So there's 24 different ways for these presentations to happen. Okay, so another thing that we can do is look at combination of numbers. So how many 4-digit numbers are there if repetitions are allowed? So remember, for 4-digit numbers, we're dealing with the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Okay, if it's a 4-digit number, okay, so it would be something like 4,127, right? 4 different digits. The criteria for a 4-digit number in math is that first digit has to be not a 0. Because if I said I have $0,112 in my bank account, you'd be like, well, why did you put the 0 in, right? That is just 112. So the key thing with a 4-digit number is that first digit can't be 0, right? This guy would be a 3-digit number. So that first digit needs to be a 1, 2, 3, 4, 5, 6, 7, 8, or 9, not a 0, okay? So we have a spot for a first digit, second digit, third digit, and 4th digit, and we're going to multiply however many options we have for each spot. So first digit, second, third, 4th. So as I said, that first digit cannot be 0. So we're going to look at everything other than a 0. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9 options. 9 options for that first digit. Then it tells us repetitions are allowed. So if we pick, now for the second digit, we can pick any of the digits. We can pick 10 digits. And then again, because repetitions are allowed, we can pick any 10 or any of the 10, right? So there's 9 options for the first one because 0 is not included, and then 10 options for each of the rest, okay? So then that's going to be 9,000 different numbers. Okay. If repetitions are not allowed, here's how this is going to change stuff. Okay, so again, we have first, second, third, fourth digit. We need to figure out how many options we have for all of them. The first one, again, it cannot be a 0, so there's only 9 options. Okay, and what repetitions not being allowed means is that, let's say we chose a 4. Okay, so 4 is now gone from our options. So now we could choose a 0. This number could be a 0, but let's say we chose a 4, or maybe it was a 5, or whatever it was. Whatever it was, it's not an option anymore. So now we only have 1, 2, 3, 4, 5, 6, 7, 8, 9 options for the second digit. Then let's say we used a 2. So now we only have 1, 2, 3, 4, 5, 6, 7, 8 options for the third digit. Now let's say we used a 9. Now we only have 1, 2, 3, 4, 5, 6, 7 options for the fourth digit. So our number of option decreases because we're not allowed to repeat those digits. Okay, so 9 times 9 times 8 times 7 is 4,536 different numbers. Okay. If the number must be odd and repetitions are allowed, we have to look at a different kind of restriction. Okay, so what it means to be an odd number is that it's gonna end in a 1, a 3, a 5, a 7, or a 9. So if we have one of these 5 numbers at the end, that means we only have 5 options at the end. If we have repetitions are allowed, that means we could pick one of those 5 numbers again for any of these spots. So then we just have to say, okay, how many numbers can go in the first spot? This can only be 9, because it can't be a 0. These ones could be a 9, or the ones that have already been picked, so there's all 10 options in the middle. So 9 times 10 times 10 times 5 is 4,500 different numbers. If the number must be even, okay, this means it ends in a 2, 4, 6, 8, or 0. So again, we've got our 4 digits. It's only have 5 options for that end, right? Because it has to be one of these even digits. And then we can't use a 0 here, so there's only 9 options. And then 10 and 10 in the middle. So this ends up being the same, right? Which makes sense, because if we look at the 9,000 numbers that there were, 4,500 of them, so half, should be each even and odd. Okay, so the last thing here we're going to look at is how many ways are there to arrange the digits 1 to 9 if they must alternate odd and even digits. Okay, so we're taking all the digits, we're putting in them in some order. Each order is going to be unique, right? A digit that would start with like a 9 is more preferable than a digit that starts with like a, I don't know, a 1 if we're talking bank account numbers. So we're going to lay out 9 different spaces this time, because there's 9 different numbers that we need to assign a spot. And the criteria this time is that they have to go odd, even, odd, even, odd, even, odd, even, odd. Okay, so the odd digits are 1, 3, 5, 7, and 9. The even digits are 2, 4, 6, and 8, right? So we're not doing 0 here. So if I look at my first odd digit, I have 5 different options. If I look at my first even digit, I have 4 different options. And then if I go back to odd, one of these 5 numbers would have had to be picked. So it doesn't really matter which one. So let's say the 5 was picked. So now there's only 4 options. And then same deal here. Let's say the 6 was picked. Now there's only 3 options for even. And then 3 options for odd. And then 2 options for even. And then there's only 2 options for odd. Then you're just down to whatever's left over for both. So this is going to be 5 times 4 times 4 times 3 times 3 times 2 times 2 times 1 times 1. So when you calculate that, it's 2880. And tomorrow we're actually going to talk about a way that is quicker to calculate this than punching in all those numbers, but unfortunately that will have to wait till tomorrow. It's not that bad. Okay, so 2,880 ways for us to arrange those digits 1 to 9 if they have to alternate odd, even, blah, blah, blah. Okay, the last few examples. So we've got 7 children, names A, B, C, D, E, F, and G. Obviously, those are very common names. They probably stand for something. We'll say that. Are going to sit in 7 chairs in a row. The children C and F have to sit next to each other, and the others can sit in any order in any of the remaining chairs. Okay, so how many possible configurations are there for the children? So when there's 2 things, and this is a really common problem, when there's 2 things that have to be together, we're going to group them together. So C and F. So I don't know, Charlie and Frank, whatever their names are. We're going to group C and F together. So we're forcing them to be together. So the way that I kind of look at this is I make them a little Scrabble tile and I put them together. So C and F. So C could sit on the left and F could sit on the right, or they could swap spots. Okay, so in just this little tile that now C and F are part of a package deal, they live together in this little package, there's 2 people who could sit in the first spot, and then whoever's left over gets to sit in the second spot. So there's 2 ways to arrange just these 2 people, right? Because we could flip where they are. Then to actually say, okay, how many total combinations there are, we're going to say, okay, now they are a package deal and they can move around between the rest of the kids. So A, B, D, E, and G. Okay, so now there's 6 individual things that we have to place in any order, right? Because A could sit over here and B, and then maybe these guys, right? Like anyone could sit on any side of the group CF as long as they're not in between them. And these guys can all sit in any order. So now we have 6 things. So again, we're going to say, okay, we have 6 things, and we have to put them in those 6, we have to take these 6 things and put them in the 6 slots. Okay, so even though there are 7 kids and 7 chairs, because these guys are kind of a package deal, maybe one of them's a love seat and they get to take it wherever they want. I don't know. Okay, so for this first spot, there's 1, 2, 3, 4, 5, 6 different options to choose from. Okay, so then let's say D sat there. Okay, then now there's 1, 2, 3, 4, 5 different options that can sit there. So let's say E sat there. Now we've only got 4, and hopefully you guys can see the pattern. Then we'd have 3, then 2, then 1. Okay, so this would be 720 ways to arrange the package deal of C and F together with everybody else. Okay, now because these things, if I switch this in here, that's an entirely different combination. So when we have a combination inside of a different combination, we have to multiply the number of times each of those can be unique by each other, and that's going to give us the total different number of combinations. So the different number of combinations, the ways for these 7 kids to sit where C and F have to be together is 1,440. Okay, if just to compare, if that wasn't true, right, if everyone could sit where they would want, then they'd have 7 chairs. 1, 2, 3, 4, 5, 6, 7. And we'd have 7 times 6 times 5 times 4 times 3 times 2 times 1, which, oh, I was going to get my phone out to calculator this, but it's recording a video. So 7 times 720, right? Because this is 720. So 7 times 720 would be much bigger than 720 times 2, right? So there's there's fewer options than there are if we just had a free-for-all, right? Which makes sense, okay? So that's just a little aside. You don't have to bother with that if you don't want to. I just thought I'd throw it in there, okay? Okay, in this next situation, we have 6 children, A, B, C, D, E, and F. They're going to sit in 6 chairs in a row. Child E must be somewhere to the left of child F. How many possible configurations are there for the children? Hint, there's an easier way to do this. So we'll get to that in a second, but we're going to think about this logically. So there are 6 spots for the kids, and start up in the top left like I have, because otherwise you're going to run out of room. So if there's 6 spots for the kids, and child E must be somewhere to the left of child F, we could put E here and F here. Well, okay, wait, hold on. E has to go here. We'll put it below, because that means there's one option for there and one option for there. Then A, B, C, D can sit wherever they want. So 4 options. So like any of the 4 of them could sit in that first spot. Then 3 who are left over, then 2 who are left over, then 1. Okay. But then what if F moves over here? So then what if we have this? And so now we have F here. So there's one option for that spot. E could go here, or E could go there. So then we've got, okay, what if E's here? Then we have 4 options times 3 options times 2 options times 1 options. But there's really 2 times all of this because it depends on where E sits. Okay, so this is going to get confusing. We're going to do one more just to demonstrate the oh my goshness of this. What if F moves here? Then E could sit in any of these 3 spots. So let's say he sits there. And then there's 4 kids to fill those remaining. Oh, F, that's a 1. So F has to sit there. There's only one option. Then 2, then 1. So 4 options, 3 options, 2 options, 1 option, the remaining 4 kids. But there's 3 there's E could sit here or here or here. So we'd have to multiply this whole thing by 3. So that just gets really confusing. The other way that we could look at this is there's a total of, if we arrange the 6 kids in the 6 chairs, we could just do 6 times 5 times 4 times 3 times 2 times 1, right? There's 6 options for that first chair, then 5 kids left, and then 4 kids left, and then 3 kids left, and then 2 kids left, and then whoever's left has to sit in this chair, okay? So that's a total of 720 ways, okay? Now, if we think about this logically, there's only 2 things that can describe E and F related to each other. Either E has to be, I guess E gets a capital, E has to be to the left, or E has to be to the right. Okay, those are the only 2 options. So because there's only 2 options, and this is a symmetrical problem, that means these would each just be half of the 720. So the easier way to do this is that we just take 720, we divide it by 2, so we get 360 different ways for E to sit to the left of F. Okay, so that's a little bit weird to think like that. It takes some practice to develop your brain to think like that. This is very puzzle based, I find. So that's why we've been working on logic puzzles and that kind of thing to help train our brains to think like this, to help us succeed. So we could have done it like this. We could have kept going and we would have gotten to the same answer. It's just a heck of a lot harder. Okay. This is a very tough question. So this would be like the hardest question on a test. I don't think the diploma would get this hard, but you just never know. Joan has 3 different English textbooks and 3 different math textbooks. How many ways can she arrange the books on a shelf if the math books must be kept together? Okay, so this is that same situation where we're going to group the math books in one kind of, I call them Scrabble tiles. So we can move math 1, math 2, math 3 around within that box, and they can go in any order. So it could go 1, 2, 3, or 1, 3, 2, or 3, 2, 1, or whatever. So you have to figure out how many different ways that we can order that. Okay, so in the first spot, second spot, third spot, in the first spot we can pick from the 3 books. Then one of the 2 that's left has to go there, and then whichever one's left over has to go in the last spot. So that would be 6 different ways to arrange those 3 books. Okay, then they're going to go as a package deal and go with the English 1, English 2, and English 3, and then math, math, math. Okay, so now we have 4 different things that we're going to have to put into 4 different slots. Okay, so of these 4 things, I have 4 options to pick in the first spot, then 3, then 2, then whichever one's left over has to go in the last spot. So 4 times 3 times 2 times 1 is 24 ways. Again, when I've got a combination within another combination, we have to multiply those. So 24 times 6, there's going to be 144 different ways to arrange these textbooks if the math ones have to be together. Okay, for practice today, you guys can read these pages in the snap book. It's not super long, just some other examples for you guys to help wrap your heads around this, and then do numbers 1 to 10 on the following pages. Okay, if you have any questions, feel free to let me know.